So today, much like we did on Friday, where we looked at some examples of AP problems involving what we're studying currently, these are extrema that show up on AP problems. So let's take a look. Cars traveling on a straight road with a velocity of 55 feet per second at time t is equal to 0. For time between 0 and 18 seconds, the car's acceleration in feet per second is the piecewise linear function defined in the graph above. Is the car's velocity increasing or decreasing, or excuse me, just increasing at t is equal to 2 seconds? Why or why not? All right, so at t is equal to 2 seconds, the acceleration is 15. So since v prime of t is equal to a of t, and a of t, or excuse me, a of 2 is equal to 15, v prime of 2 is positive, and therefore the velocity is increasing. And I like to go back at the end of this and go, they asked me a question, it's a yes-no question. So I should probably put yes or no at some point. All right, on the interval from 0 to 18, find the x-coordinate of each local maximum and each local minimum value of the velocity. Justify your answers. Okay, so when they tell you that this is the acceleration graph, they're telling you this is the graph of v prime of t. So when we're finding local minimums and local maximums, we're just going to do the first derivative, right? We're going to find the critical points. There are 2 of them, at t is 6 and t is 16. And we can tell whether those are local minimums or local maximums. So the velocity has a local, what happens at 6? Right. At t is equal to 6, because a of t, which is the same thing as v prime of t, I like to tell them that in every single part. Hey, look, I know this. Changes from positive to negative at t is equal to 6. And then the velocity has a what at 16? Yeah, a local minimum. Because a of t, which is v prime of t, changes from negative to positive. At t is equal to 16. That's about as straightforward as they can get. They did dress it up a little bit by not just giving you the graph of f prime. All right, let's take a look at this one. A particle moves along the x-axis with velocity for t greater than or equal to 0 given by -1 plus e to the 1 minus t power. So this is our velocity. Find the acceleration at time 3. All right. So I need to find the acceleration in general, a of t. And again, I like to tell people this is what I'm doing. I'm finding a of t by taking the derivative of v prime, just in case I screw up so badly that they can't tell that I've tried to take the derivative. So that's going to be e to the 1 minus t times the derivative of 1 minus t, which is negative 1. Notice they weave in that you have to do the chain rule to get this problem correctly. So a of 3 is going to be e to the 1 minus 3 times negative 1. So it'll be negative e to the negative 2. Now, if this happened to be on the calculator part, you could do that in your calculator, right? You could use the numeric derivative to get an approximation for this. It was easy enough to do by hand to where I didn't. All right, part B, is the speed of the particle increasing at time t is equal to 3? Give a reason for your answer. We haven't really talked about this yet, at least I don't think directly, but speed is increasing when velocity and acceleration have the same sign. All right, if something has positive velocity and the acceleration is positive, it's speeding up. All right? If the velocity is negative and the acceleration is also negative, right? Those are working together. So it's also speeding up. So we need to figure out, well, what is the velocity at time 3? The velocity at time 3 is going to be negative 1 plus e to the negative 2. I think this was a calculator problem, but I honestly don't remember. So let's see if we can kind of figure it out. Do you know about how big E is?
2.72.
Yeah, 2.7 something, right? So if I put 1 over 2.7 squared, that's going to be a really small positive number. Plus negative 1, that's negative. And a of 3, which we found to be negative e to the negative 2, is also negative. Therefore, yes, the speed of the particle is increasing. And part C, find all values of t at which the particle changes direction. All right, so it'll change direction when the velocity changes sign. So, negative e to the 1 minus t is equal to 0. Oh, sorry. Where the velocity changes sign. So this would be negative 1 plus e to the 1 minus t is equal to 0. So that's going to be, I wonder if we can do this by hand. E to the 1 minus t is equal to 1. Take the natural log of both sides. We get 1 minus t is equal to the natural log of 1. And the natural log of 1 is 0. So the only possibility is t is equal to 1. But notice they said justify your answer. So just showing that this is where the velocity is 0 is not enough to justify your answer. We also need to show that the velocity changes sign there. Remember, just because the velocity is 0 doesn't mean that we're going to have a change in direction. It's just a potential for a change in direction. So if we look at the velocity greater than 0, if we substitute in, let's substitute in a very large number. So this is going to be like e to the negative 4 billion, right? This is going to be a really small positive number, plus negative 1, the velocity is clearly negative. If I substitute in something like 1/2, I would have e to the 1 minus 1/2, that would be the square root of e. So the square root of 2.7, I don't know what it is, but I know it's more than 1, right? And so something more than 1 plus negative 1, that's going to be positive. And v changes from positive to negative at t is equal to 1. So my answer is t is equal to 1. Right, it's the same sort of thing when you're finding a point of inflection. When you're finding a point of inflection, you must show that the second derivative changes from positive to negative or negative to positive. Just finding a point where the second derivative is 0 is not sufficient. All right, let's go on. Particle moves along the x-axis so that its velocity at any time t for t between 0 and 16 is given by this equation. At t is equal to 0, the particle is at the origin. Sketch the graph of the velocity. So this literally was chuff this into your calculator and sketch the graph. I think this was on an AB exam. I don't think it was on a BC exam. They don't ask you to do this very often. I think that the reason that they asked it was because if someone put it into their calculator wrong, like they had it in degree mode instead of radian mode, they had a separate rubric for it on how they were going to score it. And so, but the only way to really know for sure was to have them graph it. I don't know that that's what happened, but I suspect that that's what happened. So this is very much a calculator active problem. So clear that stuff out. So we want e to the 2 sine t. All minus 1. And I want to do it on a window where this goes from 0 to 16. And heck, I'll even make it go by 4s. And the y goes from -8 to +8, also by 4s. Kind of an interesting looking graph. So you would sketch that. All right, during what intervals of time is the particle moving to the left? All right, so the particle will be moving to the left when the velocity is negative. So I just need to find the two time intervals here where the velocity is negative. So I've got to go through this. It's not terrible, but man, you feel like there's got to be a better way. All right, so this is somewhere between, say, 1 and 4. $3.14159. Hey, that's pi. And let's see, could we have figured that out? Yeah, you could do that without a calculator. But graphing it wasn't a chance. So what do you guess this point is?
2 pi.
Let's see if it really is. So let's trace this to 2 pi. Yep. It really is. So occasionally they'll do one like that. I'm curious, if you change this to degree mode, I'm wondering what sort of a graph you get. Yeah, I wonder if that's ever negative. I'm going to change my window so that my y just goes from -1 to +1. Yeah, it's never negative. It's never moving to the left. All right, moving on. Here is what I think of as sort of the prototypical AP question where they give you the graph of the derivative and they ask you a bunch of questions. So the figure above shows the graph of f prime, the derivative of the function f. Isn't that nice? They tell you that that's what that little apostrophe looking thing is on the closed interval from -1 to 5. The graph of f prime has horizontal tangents at x equals 1 and x equals 3. So you don't have to guess where the horizontal tangents are. The function f is twice differentiable and f of 2 is equal to 6. The f of 2 is equal to 6 is actually something that you would need for part C in this question, which we're not going to get to. It's for something we haven't done yet. So find the x-coordinate of each of the points of inflection of the graph of f. Give a reason for your answer. Okay, so where does f have a point of inflection? I'm going to write up here where I have a little more room. F has a point of inflection at what?
When f double prime is 0?
I'm sorry?
When f double prime is 0?
No. And the only reason I'm making a big deal of that is because I just said it a minute ago. It's not sufficient to say f double prime is equal to 0. What has to happen?
It goes from positive to negative, or the sign changes?
Right. So let's write that out to start with. F has a point of inflection when f double prime changes sign. And when is that going to happen? Because I don't have a graph of f double prime. If I talk about f double prime on this as a justification without any, connecting it to this graph, you get nothing. How can I tell f double prime from the graph of f prime? What is the definition, and I made a big deal out of this, what is the definition of f being concave up? What has to happen for f to be concave up? And don't say anything about f double prime, because it's not anything about f double prime.
When f prime is increasing.
When f prime is increasing. Right? So here, f prime changes from increasing to decreasing, or from decreasing to increasing. This happens at x is 1 and x is 4. Personally, when I do these, I don't talk about f double prime at all, right? Because the definition of concave up and concave down is on whether f prime is increasing or decreasing. So another way to do this would be to go on each interval and say from x is negative 1 to x is 1, f is concave up because f prime is increasing, concave down on the interval from 1 to 3 because f prime is decreasing, and concave up on the interval from 3 to 5 because f prime is increasing. All right, let g be the function defined by g of x equals f of x. Find an equation for the line tangent to the graph of g at x equals 2. All right, so I need to find g of 2, which will be 2 times f of 2, which will be 2 times negative 1 is negative 2. G prime of x, and again, they're testing can you do derivatives. We've got to use the product rule. It'll be x times f prime of x minus f of x times 1. So g prime of 2 is going to be 2 times f prime at 2 is negative 1. Oh, sorry, back up just a second. F of 2 up here is 6. I was looking at the derivative. This is 12. So this would be f prime at 2 minus f of 2 times 1. So that's going to be 2 times f prime at 2 is negative 1 minus f of 2 is 6. So that's negative 8. So y is going to be equal to 12 minus 8 times x minus 2. So I apologize. We did end up using the f of 2 as 6 for this. All right, let's take a look at this one. Let f be a function that's continuous on the interval from 0 to 4, inclusive of 0, but not inclusive of 4, which is interesting. The function f is twice differentiable except at x is equal to 2. Okay. The function f and its derivatives have the properties indicated in the table above, where D and E indicates that the derivatives of f do not exist at x is equal to 2. So, on the interval from 0 to 4, find all values at which f has a relative extremum. Determine whether f has a relative maximum or a relative minimum of each of these values. Justify your answer. Okay? So, we would need to be looking at critical points. Critical points are going to be where the derivative is 0 or where the derivative does not exist. There's only those two critical points. Notice it doesn't say find the critical points. They could have asked that. So at x is equal to 1, what do we know about f?
Stays positive.
Yeah, has no relative extrema. So you don't actually have to say that because it said find all values where it does. Right? I do it anyway just because I'm thinking about the critical points. Doesn't get you any points. And then at x is 2, what happens? What does f have?
Local max.
Yeah, a local maximum. Because f prime changes from positive to negative. On the axes provided, sketch a graph of a function that has all the characteristics of f. So 0, we're at negative 1. At 1, we're at 0. At 2, my function is at 2. At 3, the function's back to 0. We don't know about 4. So on this first interval, we have a positive first derivative, function's increasing, but a negative second derivative. That means that the function is concave down. So that's got to look like that. On the next interval, both are positive, so it's got to look like this. Increasing concave up. Then I want negative concave down. So that's going to look like that. And then I want decreasing concave up. So decreasing concave up would look like this. And I know that the first derivative is 0 at 1, so that means it's got to do something like this. It's got to flatten out at 1. Then here I go from decreasing concave down to decreasing concave up, so it's going to go overhand, underhand. We used to call this the shark fin problem because that's what it kind of looks like. Okay? Any questions about those? That's just sort of a smattering of the kinds of things that you could be asked.